presentation at ODAC APA 2023 is about applied reinforcement learning for online ads recommender, where I'm sharing a bit of my past experience and current activity. So to give a bit of context, a key learning point, the presentation is kind of a bit dense, and we will talk about a very diversified content for this session. But just to help a bit the people who join who are maybe less familiar with this topic, I think the key point to remember of this session is about the business context and the tech impact of our ad and recommender in the overall tech industry. The second part is about the role of data science and machine learning, especially in ad and recommender. Data science and machine learning are a bit separate fields. There are a couple of machine learning tech challenges. And last part is which is the core of this presentation, is about reinforcement learning for ads. On one side is about the fundamentals, and on the other side about the real-world application to practice. Yeah, I think this session also is the opportunity to learn a bit different perspective of ML that we cannot find online or maybe in other conferences that you cannot find with ChatGPT. Especially, you may get some insight about the geospatial use cases and about use cases in Japan. So the presentation, as mentioned, is split in three parts. One is about the context of online advertising tech. Second is about the applied machine learning data science in that field, especially the tech challenges and the data stack. Third part is about the applied reinforcement learning, the fundamentals, some real-world example, and overview of the tech stack use, especially the PyTorch part. So let's go into, so in a bit of background on my side. I have been working in financial industry initially, so I have a very good experience in stochastic modeling, which is very common for reinforcement learning. The base of reinforcement learning is about stochastic and probability modeling. Yeah, I went into big data machine learning when I have to manage advertising recommendation. And currently, I'm using this kind of experience for geo ad solution at MyBot Japan as the head of machine learning ads. Just to give you a few words about the context, MyBot Japan overall, maybe you never heard about MyBots, but in fact, MyBots are very large user reach. More than 700 million of monthly active users using MyBots the maps, and more than 40,000 mobile apps using the maps. And SoftBank is a major investor. So probably you have used MyBots map without knowing it was a MyBots map. And more specific for the Japan is they are developing zero ad solution for corporates, typically for Yahoo Japan map. And also a couple of geotech solutions for corporates, focusing on real-time and large-scale services. If you want to have a bit more news, you can email me or go directly to the website. So let's go into the presentation. So in terms of the context, the ad spending in the digital advertising market is more than 600 billion US dollars. It's very huge. Asia Pacific is around 200 billion US dollars. And of course, you have very large tech actors, Google, Meta, and Amazon. But you have also a lot of more regional players, usually by countries or by industry. Typically, Yahoo Japan in Japan, Baidu in China. Every country has their own kind of large tech advertiser. But all of them as a common point is they invest a lot in online ad technology at any level, as a data stack, ML stack, and they open source a lot of their technology development. So you can take about TensorFlow come from Google, and Google rely on ads, PyTorch from Meta. So a lot of driver of the big data trend in the 2000 came from the ad tech company. And a lot of trend of the development machine learning tech since 2010 and more recently also come from open sourcing from ad tech companies. So ad technology has not only impact on the ad, but also on the whole tech industry. To give a bit of some words about Japan, Japan is very mature market. They also have very large online spending. Largest online ad publisher are Yahoo Japan. Maybe Yahoo Japan, in fact, is on par on traffic than Google. Maybe people doesn't know. You have Line, who's the largest social media app, and also a couple of e-commerce like Rakuten, Amazon, and a lot of local Japanese publisher. So Japan has very large retail consumer base, and that's why the online advertisement ecosystem is also very dense. A couple of comments about geo-targeting. Geo-targeting is a sub-field of online ads. You have very large player, Google Maps, and you have a lot of specialists, usually by country or by mobile app, typically. You have two types of services. One is called online to offline. So you bring online traffic, which is typically web traffic, into physical location on the map. And you have a reverse, which is offline to online. So you bring location search into online services, typically e-commerce. And of course, you have a mix between both services. And from a technology perspective, you need to combine both of them, especially the technology stack between ad and geospatial data are very different. Also the people too, kind of big challenge. And also you have the real-time part. That's for the context. So I will go into the ad challenges. So when you work on production level advertisement, you have two key factors. One is called scalability, because you need to handle potentially very large user base, maybe 10,000 to million, and maybe some of them billion. And at the same time, very large inventory of ads and items from 100 to million. And at the same time, you need to have response time in milliseconds to display. So every improvement for the customer, for the end user, like lower latency, have higher cost. If you add more personalization, personalized targeting, also you need to handle higher data volume. So everything will be higher cost. So you have to manage the increase of cost with the increase of benefit. Is applied same for the machine learning. When you try to apply some new machine learning approach, let's say GPT or whatever, we also evaluate the cost and the benefit in actual revenue. So for machine learning, everything become more challenges because you have higher latency for machine learning compute, higher also compute needs, GPU. You need also to redesign a lot of data pipeline. You have a lot of constraint on model, type, size, complexity, and a lot of extra. So everything just become more complex with machine learning on top. It's good to keep in mind. So in terms of the data science and machine learning use cases, so just in few words, data science is more focused on kind of decision science. The end decision will be done by human, roughly, very roughly. And of course, you can use machine learning tools, statistical tools to get your decision, but at the end, the human person will take the decision. In machine learning, bit the reverse, so the end decision will be done by machine, which is automated, kind of automated intelligence. And to support both of the kind of field, we have data engineering, we do data pipeline. Of course, data science and machine learning are a lot of overlap. And but in typical ad recommender domain, if you go to the big tech or smaller tech, it is usually divided into fields like this. So this table summarizes two approaches: data science focused on evaluation, estimation, decision done by human, and machine learning focused on automation and productionalization and science part. And data engineering is just everywhere. Everybody, in fact, is just at least 50% a bit data engineer. So the typical data science use case in ad recommender is usually split in two parts. One is called pre-experiment. Before we start advertisement campaign, or we need to spend time on feature engineering, analysis of data for user segmentation, and a methodology for evaluation, A/B test, KPI. And you have the post-experiment part. Typically, the analysis of A/B test, mean estimate of the metrics. And a bit more recently, the causal identification means that we need to have some define some causal graph based on the experiment. So we can define new hypothesis, a new experiment, a new metrics. This is a typical workflow on data science. On machine learning side, contrary to the image, ad recommender system is not just one model fitting one model, it's just myriad of interconnected systems. Each system can have one or two models. Typically, we need to transform all the input data into vector or sparse or dense vector, so it can be consumed by machine algorithm. If you have text data, you have some data processor. If you have image data, you can have another data processor, same from time series, same from tabular data. And for every data type, you can have 10, 100 type of processing type. So we make increase the complexity. And in terms of recommender, and you have many approaches. Some of them is called a sequential based, session based, context based, graph based. You have a lot of them. And today's discussion is more about the reinforcement learning based. So I just give you one example of data processor. So it's called neural net. It's mostly to encode the image into a dense vector. It's called variational autoencoder are used in the past, usually to encode some image with some kind of semantics. Even if it's used in neural net, we can call it as a data processor because it will transform raw image into vector. Another type of data processor is when you have an NLP test. You can use some bear type model plus some embedding modeling to output some vector base. We can use those vectors into the commander ad system. So typically, data processor can be very complex model itself. Okay, so I will mention about the data stack as online advertising. So this is a bit simplified view on the data stack and data pipeline we usually face, but is I think summarize well what we need to manage. On the top left, you have the raw log, top left raw log, which is a click and impression. Usually we receive it as a streaming, the streaming for the UI. It is usually stored in data lake. Can be Amazon S3, Azure, or Hadoop for people. Any kind of data lake, just store it. And from the data lake, we connect to the SQL database. There are millions of SQL database, Redshift, MySQL. And just SQL database feed typically BI tool or some kind UI for data science or SQL analysis, typically A/B test analysis. Can also feed machine learning flow, but for machine learning flow, it does not always rely on SQLDB because you can have high cost. You directly feed directly to the data lake as well as the streaming. In machine learning flow, you also connect with another type of database called key-value store. And the reason of using key-value store, you can have access of the data instantly without any processing time. And at the end, you have the ad serving, just the system, backend system, which just provides the display to the actual ad. So this schema is very typical of the kind of ad recommender system in all the tech industry. So if we zoom a bit, I will zoom a bit and I will just go into the machine learning flow. So for machine learning flow, you have two types of machine learning flow. One is about the training. The training required high volume of data, a distributed kind of training. because sometimes the model can be big, the data can be big, you need to have distributed. It typically is directly plugged to the data lake on the top. You have like mini batch processing with some framework like Petastorm, Ray, and you directly feed from the data lake. You have another machine learning flow is called inference. When you do the prediction, we want to have low latency. So in order to have low latency, you need to use the k-value store directly because latency is very low. And more recently, you have a vector database. Vector database is very similar to k-value store, but you can store embedding, and you can have a similarity embedding processing. And all this kind of template data, we can process gigabyte, terabyte, even petabyte of data relatively fast. That's the data stack. So I jump into a bit the geospatial use case because this is my current use case in my bots. I just explain the key part of geospatial data. The key part of geospatial data is to identify location. You can see on the light, you have the map is divided in 4 parts. Each of the square is identified by integer. And we need to partition the map into fast identification by integer. And with this integer hashing, we also integrate the zoom level. So we can fetch area of location very fast. And that's the key part. So this is called tile system, when people are a bit familiar with geospatial data. You have also different tile system on the left. It's called hexagonal. It's Uber using this kind of partitioning of the map. Everybody has their own kind of partition. In that slide, I just mentioned 3 of them. It's called quad key. You have Uber and S3. All of them are pro and con, but all of them are based on integer type identification of the map. Make things the fetching very fast. Usually, those kind of identifier is fed into the machine learning side, so we can integrate the geospatial data as an input for the model. That's the overview. So I will jump into the main part of this presentation is about reinforcement learning, and we'll go into more the fundamentals. So typically in the machine learning, when we deal with tabular data, which is the standard input data for ad and recommendation, we have 2 types of methods. One is called supervised learning. Typically, we have some label and we want to predict the label based on some input data. Yeah, having label usually costly and slow and issue, some issues. And we can have also overfitting. The other way is unsupervised learning. We need to find some patterns cluster on the data. It's mostly pattern recognition. It's not necessarily prediction. And the main issue is to have some distance metrics, correct distance metrics. This is very standard, and probably most of the people are a bit familiar with those 2 approaches. But in reality, you have many ways to learn from data. It's called learning processes. So you have the supervised learning, unsupervised learning. More recently, you have self-supervised learning, which is used for GPT training, especially for NLP. So you don't have to have explicit label, so you have implicit label by masking the data. You have reinforcement learning that we will mention today, differential learning, meta learning, transfer learning, adversarial learning, structured learning, especially for causal graph learning. You have a lot of ways to learn from data. Each way of learning of data provides some kind of insight of the data. So I think this kind of information of this kind of thing is not usually mentioned in conference because usually people focus on unsupervised learning or unsupervised very specific part. But in fact, you can combine different ways to learn from the data. So to come back to our core discussion, reinforcement learning is a kind of process we have interact with the environment. So the prediction, the machine learning model will predict some action. And the action will take, will do some action and some intervention on the environment. And the environment will provide back some reward. Like typically in chess, you play some play and you receive win or loss. So typically, you have reward from the environment. So it's a sequential and adaptive learning that every time you do some action, and based on the reward, it will update your action in the sequential way. So you have the feedback loop, which is fundamental in that process. Having a feedback loop helps to handle better the data and environment drift because you have dynamic learning process. You do some prediction, you receive the reward, fail or pass, and next time you will adjust. You will try to reduce the overfitting, underfitting process because you can adapt to the data. Typical overfitting is happen with the supervised learning and underfitting probably with unsupervised. But the main challenge of reinforcement learning, when you go into the research paper or into very details, there are many schools of reinforcement learning. If you go at university, it's separate in very different academic field, even the research paper. If you go in the machine learning conference, it's still separate in different way. One of them is called optimal control. Another model free is stochastic bandit is another way of reinforcement learning. So you have many different schools. They all use their own vocabulary, even though the fundamentals are very same. So it's make sometimes people confused, in fact. Because they think the reinforcement learning in some way, but in fact other people are doing other way, and it's kind of a bit challenging to go into the details. So I will try to just summarize the key parts, so at least people will get a bit of insight when you read some research paper or some specific article. People will have at least grasp the main point. The main part of reinforcement learning is to learn a policy. A policy is, you can say that the decision algorithm. It's the algorithm who takes the decision to take some action. Usually the policy is probabilistic, stochastic. So we try to learn the probability of taking this action based on some state. So in order to optimize this action, you need to have some reward. So technically you have different reward definition. You have next step reward. So you take some action and you will receive on the next step some reward. And you have also the total reward, which is all future action and all future state. You do sum all of them and you take the expectation of all of them and you get the expected total reward. And the role of the reinforcement learning algorithm is at the bottom of this slide is to learn a decision algo who will maximize the total expected reward for all possible action and for all possible state. So you take the average maximum. That's the goal of reinforcement learning. And so in order to solve this kind of, because it's very generic formulation of the reinforcement learning, so this one can apply to all kind of reinforcement learning. It's very generic. You have little assumption about this formulation. So in order to make it solvable, you need to have a couple of technical properties, which is called Markov property. That's the current optimality only depend on current state. Every stochastic variable is just dependent on current time. It does not depend on the past. Based on this property, we can have a very nice decomposition, mathematical decomposition, that the best reward is the current reward plus the sum of future one. It makes it the reinforcement learning can be solved in a mathematical way nicely. So if you go into the literature, you have a very large literature about to find best policies called Q-learning, policy gradient. if some people have a lot of interest, you can go in the Google DeepMind papers. They publish a lot. And they all have a different kind of approaches. So this is kind of fundamental. I think just is good to keep in mind those basics. And how it is applied in ads. So that's the core of the presentation. Is the main challenge when you apply this kind of reinforcement learning for ads and recommendation is the latency. Because at the prediction time, you need to simulate all future paths. Your model has to take all future paths and take the average. You have high latency cost and high compute cost. It's not feasible because if you have to do for all million users in real time, it's just impossible to compute. So what people are doing, we need to simplify the assumption. It's called, when we simplify the assumption, the reinforcement learning problem comes back to problem that's called stochastic bandit. And we just remove some state of the action and we only focus on the action and the next step reward. We don't do simulation of the future. We just say we take some action and we receive some reward. Typically click, no click, buy or no buy. And the funny thing is the bandit theory has been developed outside of reinforcement learning school. Most people usually they don't talk each other in academics. Usually they are different people. And bandit usually use their own vocabulary, different from reinforcement learning, even research paper too. And usually they are a bit domain application are different. Reinforcement learning people will call it reinforcement learning in robotics, in game like AlphaZero. But for online ads, people prefer to call it bandit, whereas it's still reinforcement learning. So just to be careful of when you read research paper. So in the bandit reward, we only focus on the action and reward pair. That we take some action and we will receive some reward. And the action is called arm. That's why it's called multi-arm bandit. Another assumption in bandit is, as I mentioned, usually in bandit they use different kind of metrics, and one of them is called a regret. To make it very simple, regret is the number of mistakes you make every step. So you assume you know in theory the optimal best decision at each step, and you compare your current decision with the optimal best one. So every step you can count the number of mistakes you have made. If this is the total regret over time. And what we don't want to make too much mistake over time. We just want to have the best decision at each time. So if you make mistake at every step, your regret will increase linearly. So every step you make some mistakes, so it's just linear. So what we want sublinear regret, that we don't make mistake at every step. That's just the way to measure it in bandit. If you go into the research paper, you will have this kind of regret formulation. So another part to apply reinforcement learning for ad recommender is we need to add back some state. Technically, because we need to make sure the reward is dependent on some context. Typically, the context of the reward depends on the time, like the day of the week, or day of the month, or location, type of user, married, not married, type of the item is the price of the item. So you can have a lot of context. Based on the context, your reward this can be modified. So having this kind of state and context state help to have more precise reward and more accurate feedback from environment. Typically, the contextual bandit are the most used reinforcement approach in reward ads and recommender. This is the approach used. If you have a lot of variation of the contextual bandit, usually people do variation of the context or the variation of the reward formulation, but all of them are based on this kind of formulation. I give quickly one of them. It's called Thomson contextual bandit. So instead of we assume some probability distribution of the expected reward, and we can use some Bayesian setup. Usually we update the posterior with some data, and we sample from the posterior distribution, and we get some estimate of the best action. Benefit of using Bayesian setup, we can handle better the uncertainty, especially if we have very low traffic for some item or some area. Bayesian setup help to handle this uncertainty in the more natural way. Okay, so it's time to go into some example so people can figure out where it is used and how it is used. So if you use your iPhone, if you go on the iOS App Store, App Store, you have a list of suggestions. Usually use bandit. Apple use they have a 2-layer bandit. And for the search and suggestion in iOS App Store. Why they use a 2-layer bandit? Because you have number of apps is very big in iOS. Having the 2-step bandit just help to have more precise recommendation. One is focused on the metrics called recall, and another part is called focus on the precision. People can have a look. I think their paper is online. It's quite interesting approach. Another typical use of reinforcement learning for ads is for the banner. When you go on any website, Netflix or whatever, you typically use some bandit to display the banner. You have a 3, 5, 6 banner, you have banner rotation, and usually the banner rotation is optimized based on the past action of the user and using some approach. On our side in Mailbox, we are using some bandit algorithm for Yahoo Japan map to display some advertising icon. So this is the image of Yahoo Japan map. Just to give some context, Yahoo Japan is one of the most popular website service on par with Google. And they are very popular retail map using the Mailbox tech. Okay, so just quick word about the evaluation methods. So you have 2 types of evaluation methods called online and offline. Online is the A/B test. And offline is when you do the model training and you do simulation using past data. And the goal of offline is to correlate with online metrics. It's very useful to have offline metrics because you can iterate your model faster. So you have a lot of methodology. All are based on resampling method. You need to resample your past data to make sure you remove a lot of bias. This is very active research field. If typically in conference, in specialized conference machine learning, you have a lot of paper about this field. So I will just go into the technology stack quickly. On left side, you have the data stack. And on the right side, you have machine learning stack. Data stack can be on-premise, on cloud. Data stack usually is based on data lake, NoSQL database, and SQL database. And machine learning stack is mostly based on Kubernetes. And on top of Kubernetes, you can have PyTorch or lots of framework. Typical use is Spark. Spark is heavily used for big data. More recently, people use redistributed. Redistributed is now overtaking Spark for a lot of jobs because they are much more designed for machine learning and more integrated for deep learning framework. So usually you don't have one size fits all approach. Really depend on where you are on premise, on cloud, where your data stack is. You can have different type of technology stack. The main part is the data stack are often legacy. You cannot change the data stack most of the time, just legacy system. But machine learning stack are much more flexible and portable because you need to base on container Kubernetes. So it's much more easier to develop new machine learning stacks. And the difference with machine learning, standard machine learning pipeline and reinforcement learning, in reinforcement learning, you need to have near real-time feedback loop. So you need to follow the Markov assumption. If you don't have near real-time feedback loop, you can have biases in prediction and mismatch for the reward. Suppose you have the reward one day after, you cannot match your action, your prediction reward easily. That's the main issue, to have alignment of your action, your prediction, and your reward on that action. It makes the data pipeline collection, data collection much more heavy. Just another word about the tech stack quickly. You have a lot of latency issues to deal with, and also scaling cost. When you start to scale a lot, you cannot have any model as you want. You just become too costly. So we need to have a lot of restriction on your possible model. So I will jump into the PyTorch part. So I'm using PyTorch now in my boss. I'm using also PyTorch in the past. PyTorch is very active and very flexible. You have a lot of ecosystem. And the main issue with PyTorch Python is latency in the prediction time. For the training part, you have a lot of distributed framework, Torch, DeepSpeed, Accelerate. Rain now are the framework, so you have a lot of framework for distributed. But for inference, you need to another type of framework is called compiler. Then you need to compile your PyTorch code into binaries. And you have two types of binaries. You have called Torch script or ONNX, managed by Microsoft or another compiler, TVM. And those compiler works well, but for reinforcement learning, it's much more challenging because those compilers are mostly designed for NLP, computer vision operator. Typically, they are designed to optimize convolution, attention layer in neural net, but they are not designed for reinforcement learning perspective because reinforcement learning mostly use distribution. And sometimes we need to rewrite some native code PyTorch. So I have myself recode some part. Typically for beta distribution cannot be compiled. So we need to have some different approaches. So just an example of refactor code in PyTorch to make it compatible with the compiler. So I go into takeaways because we are going a bit out of time. So it's very dense presentation with a lot of topic and motion. So feel free to ask questions after directly to my email for in-depth discussion. So mostly what to remember that the online ad is a major driver of the tech innovation in the data in the machine learning. And data science and machine learning are a bit separated in the ad and recommendation. And you have a lot of constraints about latency and scalability in the production. And when you have additional data style, typically zero data or other type of data, you need to have a custom data pipeline. Yeah, the extra work. And about the reinforcement learning, just to keep in mind is we predict some action and we collect the feedback. It's kind of a feedback loop. And to make it very scalable, we need to simplify a lot of assumptions to make it the most simple way so we can scale reinforcement learning at a much larger scale. And at the end of the day, everything comes back to the evaluation process. So you have to evaluate your pipeline, your prediction, and all your correctness of all your pipeline. I think that's pretty all. I will just go into the question. I'm not sure if you have some question or not.
Yeah, thank you, Kevin. As of now, there's no question posted. But let's see. Let's give them a couple of minutes. Maybe someone will be typing in. But
I will just put my email. So if you have in-depth questions or more in-depth question, you can just send me either in this chat or in my email. So I'm happy to reply to some question in details. So if you have a bit of time, a few minutes time, I'll just go back to the PyTorch part. I'll just keep a bit quickly. Yeah, so in PyTorch, the main part to go in production is to use a compiler. It's very active field. Also driven by big companies like Microsoft. AWS also has some compiler. You have Apache one. A compiler has the benefit to have the prediction PyTorch model on CPU and on GPU, even on mobile. So this is very active topic, and this is a way to improve the Python issues in production. And to invite people to go into more the compiler part, which is very interesting framework. Also for the training part too, training also very active. Microsoft too, and you have also Ray framework, which also very active these days. A lot of people are moving from Spark to Ray these days because it can handle better deep learning pipeline. So it's still a very open field, so there is a lot of area to explore, and very interesting forward. Okay, so I think I have covered most of them. So I think people will probably need a bit more extra time to digest everything. It's very dense, but hope I think you enjoy ability to have a bit of insight in this area and invite people to discover more by themselves. Okay.